Good afternoon, everyone. Welcome to this talk on copulas. I'm going to be covering quite a bit of ground today, but I just want to give a little bit of background first. I mean, one of the things about copulas is it's one of those subjects which seems to strike terror into the heart of actuarial students, and there's always something which does that. I mean, when I was an actuarial student, it was the entire life syllabus and also age definitions in exposed to risk. So you had things like age last birthday at the policy anniversary before there's a new moon in Aquarius or something, and those types of questions just terrify people. And copulas seem to have a similar effect on some students today, and they have the perception of being very difficult. So what I'm going to try to do today is to show you that they're not necessarily that complicated if you can understand the rationale behind them and how they work. So what that means is there's a lot of stuff I'm not going to be going into at all. I'm not going to be talking about things like Sklar's theorem, for example, which actually defines what a copula is in mathematical terms. I'm not going to be talking about Scarsini's axioms of concordance, which are very important when it comes to talking about things like correlation and which measures are better than others and why. I'm not going to be talking about the Frechet-Hufting copulas, which basically tell you how the bounds within which a copula has to mathematically lie. Now, these things are all very important and they're very useful. If you want to properly understand copulas, you need to understand how all these things work. But they don't really help you understand the basics of what a copula is and how it functions and why and where it kind of sits in the sort of mathematical modelling spectrum. So I'm going to be looking more at that and also covering quite a lot of background, because and a lot of this I'm sure will be very clear and very familiar to a lot of you, but if you don't understand this background and you're not completely comfortable with it, it makes copulas much more difficult. So if you do understand this background, you can kind of see how the stuff which is more familiar translates over to this slightly less familiar world of copulas. Now, I have been told to ask people to like and comment and subscribe on this, and then to leave a brief pause for you to do it. The main reason being, the more people that subscribe to the YouTube channel, the more I'll see that people actually enjoy looking at this sort of stuff, and the more likely I am to do some more of them and take additional requests. So if you do like it, please like it and subscribe. So anyway, let's move on to the order of business. So as I say, an introduction to copulas, and this is just an introduction to give you a feel for how these things actually work. So I am going to be starting right at the very beginning, right at a very basic level for most people, which is going to be univariate continuous distributions, because this is something which you need to be completely comfortable with before you can move on to anything more complex. So apologies if this is blindingly obvious for many people, but it is the best starting point. So here we have some probability density functions, and you'll recognise these as normal probability density functions, and we have three of them here with different parameters in for means and standard deviations, and you can pick any number, and that will give you an idea of how likely that number is to occur. So x1 lying there, x2, x3. So the probability density function tells you broadly how likely something is to occur at different points in that distribution. So x3 is more likely to happen than x2 because it's higher, it's more dense there, more observations likely to be found there. x1 is the least likely, kind of. I mean, in fact, the probability of having an observation x1, x2 or x3 in the normal distribution is 0 in all cases, because they're all points and this is a continuous distribution. So for a continuous distribution, the point of anything happening at any particular point is 0. What you can do with a probability density function, with a continuous distribution, is look at the probability of something happening up to or past a certain point. So if we take x2, for example, we can look at the probability of some random observation being less than x2. And that's found by looking at the area underneath the curve here. So something else as well I should mention is for any probability density function, the area underneath the curve is always 1. So what that means is, where you've got a probability of 0 is impossible, a probability of 1 is certain. That means that if something's going to happen, it's got to lie underneath that curve. So the area underneath each of these curves is 1. The probability of something being less than x2 on this middle curve here is this area shaded here, and that is less than 1. It's the probability that x is less than x2. So what does this mean exactly? Probability that x is less than x2 means the probability of some random observation x, some number plucked out of thin air, is going to be, or from this particular distribution, is going to be less than or equal to this number x2. You can also look at the chance of something happening between a couple of points. So you can look at, say, the probability of something happening between x1 and x2, so this area here. So this is the probability that x is greater than or equal to x1 and less than or equal to x2. What does that mean exactly? It means the probability that some random observation x plucked from this distribution is going to be greater than or equal to x1 or less than or equal to x2. So this all should be hopefully fairly familiar and should make sense. You've got an area under the curve which is 1. If you take part of it, it's going to be less than 1. And that area, where you kind of segment it off, that tells you the probability of something happening up to that point. And you can also work out the probability of something happening past that point, of course. Just take 1 minus your number. So go back to this first one, probability of x being less than or equal to x2. Can we describe this any differently? Well, we've already said it's a probability of some random observation x being less than or equal to x2. We can also say it is the integral of the probability density function between minus infinity up until x2. You're just integrating the area under the curve. And we can call this something else. We've got big F of x2, capital F of x2, the probability distribution function. So those three curves that we had before, the area underneath them was equal to 1. If we look at what happens if you integrate each of those up to a particular point, you get these three curves here, which are the probability distribution functions. So what that means is, if we were looking at, say, x2, instead of having to look at the area under the curve, you just look at x2 on the horizontal axis, draw a line up to that curve, look across to your vertical axis, and that tells you what your probability is. So whereas the area under the curve went from 0 to 1 the further to the right you went, here, if you just read off this bottom axis, you're looking to see what your probability is by reading off the vertical axis, and that goes from 0 to 1. 0 is actually reached at minus infinity, 1 is actually reached at plus infinity. You can see you get pretty close within the bounds that we're looking at here. And you can do the same with looking at the probability of something happening between 2 points. The probability of something lying between x1 and x2. You could describe that as being the integral between x2 and x1, or the integral between x2 and minus infinity less the integral between x1 and infinity, or f of x2 minus f of x1. So you can go back to this chart again and you can say, well, just read off to find out your distribution function for x2, read it off for x1, and subtract f of x1 from f of x2, and that gives the probability of some random variable lying between x2 and x1. So, the probability distribution function, the features of this are as follows. The first is the input can be anything subject to the limits of the distribution. So, for example, if you've got a normal distribution, the input can be anything from minus infinity to plus infinity, and it will give you a valid probability. So if you've got, say, a distribution of people's heights, you can calculate the probability that someone is less than 15 feet tall, and it will come out to presumably pretty close to 1. You can also calculate the probability that someone is less than -3 feet tall. It actually has a finite probability if you use the normal distribution. That should be hopefully pretty close to 0. Got a log normal distribution. The input can be anything between 0 and infinity. So if you're trying to plug a negative height into a log normal distribution, you get an error. And for the gamma distribution, it's between 0 and infinity, the beta distribution between 0 and 1, and so on. So you have, so long as the input is within the limits of whatever a particular distribution can have, it can be anything at all. But the output is always going to be between 0 and 1. So f of x, capital F of x, always lies between 0 and 1. That is what a distribution function does. So hopefully everybody's with me so far. This is reasonably straightforward stuff. We're looking at a univariate continuous density and distribution functions. And just to summarise, density functions here on the left, the area underneath them is 1, distribution function on the right, they run from 0 to 1. They're essentially integrals up to the point that you're looking at on the horizontal axis. So we've done univariate distributions, let's move to bivariate distributions, bivariate continuous distributions. And of course you can generalise from a bivariate distribution, in many cases you can generalise from a bivariate distribution to a multivariate distribution. But a bivariate distribution is the best place to start, it's easiest. So here are some bivariate density functions. All we've really done here is we've taken what was 2-dimensional and pulled it into 3 dimensions. So instead of having that nice smooth curve which runs up and runs down, we now have a cone. And you can see there's an additional parameter here which is ρ, the correlation coefficient. And the correlation coefficient does have a big impact on the shape of that cone. So if you remember the curve that we had for the probability density function, the area under that curve was 1, and that was in 2 dimensions. So you move from 2 to 3 dimensions, and instead of talking about areas, you talk about volumes. So what you have here is a volume under that cone, which is equal to 1. So the further you move from negative to positive on either the x-axis or the y-axis, the greater the volume that you're kind of covering. And the 2 diagrams on the bottom, they're essentially slices through those cones. So if you imagine that the top 2 diagrams are a landscape, the bottom 2 diagrams are essentially a map of that landscape. They're essentially contour lines for those mountains in the top. So when we were looking at the density functions before, you'd look at, say, x1, and you'd be able to say, well, what's the probability of something being less than x1? Well, here, because it's bivariate, you've got x1 and y1. So what you'd be looking at instead would be the probability of something being less than, where x was less than x1 and y was less than y1. And you can find that by marking x1 on the x-axis and following that line up the hill there, and looking at where it intersects with the line that you draw from y1 on the y-axis to this point here, and then looking at the volume that lies beneath the curve at that point, because the volume under that curve is the probability that x is less than x1 and y is less than y1. So does that make sense? You've got a line that you can draw from x up that curve there, a line you can draw from y up there, where it intersects. If you look at the volume under that, so if you imagine this is like a large bizarrely baked cake, and you took a slice of cake out from that side, the volume of that cake is the probability that the observation x is less than x1 and y is less than y1. And the total volume of that cake is one unit. So as I say, to think about this, you need to think about it in volume, in terms of volume rather than in terms of area. So the probability that x is less than x1 and y is less than y1. or more precisely, the probability that some pair of random observations, x and y, are less than or equal to x1 and y1 respectively. Or you can think of it as being the integral from minus infinity to y1 and minus infinity to x1 of the density function f(x,y) dx dy. Or f of x1, y1, the joint probability distribution for x1 and y1. So what that means is, just go back to here, if this is the density function, this is the equivalent to the curve that we saw for the univariate density function. If you integrate, then you can do exactly the same thing as before. You just need to integrate across 2 dimensions. Oh, that's one thing I was going to say. What you can also see is if you've got x1 and y1 here and a correlation of 0.7, you get this area here. If you just look at where that would lie on this chart here, x1 and y1, you see the probability will be very close to 0, because the correlation means that they're negatively correlated. You're less likely to see values below that given value of x and y together if they're less correlated. So the volume of under there is going to be very small compared to here. So that's the impact of that additional parameter, the correlation parameter. So if you integrate those that cone for x and y, instead of getting a line which goes gradually upwards, you get this hill which goes from 0 as you disappear off to minus infinity on both the x and y axes, and to 1 as you head towards plus infinity on the x and y axes. So as you can see here, around the edges, which is where you get into minus 3 or past minus 3 for either of these two, you can see the probability is very low. As both of these increase, you can see the joint probability increases. So if you were to have probabilities of x1 being less than or equal to 3 and y1 being less than or equal to 3, it's going to be pretty much 1. Whereas if it's less than or equal to minus 3 for both of them, it's going to be pretty much equal to 0. And the way that you would find that out is you take x1 and you follow that line up there. Then you follow y1 and you see where that line intersects with x1. And then instead of looking at any sort of area and volume underneath anything, you simply take that point in 3D space, draw a line over to the wall at the back, and then read off the axis. And that number there will tell you what the probability of x being less than x1 and y being less than y1 is. So can we say volume is always representative of the joint probability? Is a question I've had. Yeah, for the density function, for bivariate, yes it is. So all of these things depend on the number of dimensions that you're using. So if you're looking at a univariate distribution, it's the area under the curve. If you're looking at a bivariate distribution, it's the volume under the shape. If you're looking at a multivariate distribution, then you need to be able either to visualize higher dimensions or just rely on the maths. I think the easiest thing to do is to recognize that when you move from 1 to 2 dimensions, you can kind of see what happens in terms of moving from an area to a volume. So it's just taking an analogue of that when you move to higher dimensions. But if you have a distribution function, you don't need to worry about that. If you've gone from a density to a distribution function, or you work with a distribution function to start with, which is something we'll see you can do later, it's just a case of plug in the numbers, x1 and y1, and read off the result. So you just plug x1 and y1 into the distribution function, and that will tell you what the probability of x being less than x1 and y being less than y1 is for a given correlation. And you can see again here, x1 and y1, if you had them on here, you'd be very close to the base of this cube. So when you went to the back wall, you wouldn't be very high at all, and you'd have a much lower probability distribution. So, the features of the distribution function. The input can still be anything, subject to the limits of the bivariate distribution. So, for the normal distribution, it's still going to be between minus infinity and plus infinity for all of the observations. For the log normal, it's going to be between 0 and plus infinity for all the observations, and so on. But the output is still always going to be between 0, which is impossible, and 1, which is certain. So inputs can be anything at all, constrained by the distribution. The output is always 0 to 1. It's a distribution function. So that's the basics. Hopefully that's all understood and you can see what I was getting at with the various visualizations there. Because if we understand that, then it's not too big a move to get from a bivariate distribution to a bivariate continuous distribution to copulas. So the first thing we need to do is the first thing I like to do is to look at how you can deconstruct a bivariate continuous distribution. So let's think about the characteristics of a bivariate distribution, and the one I want to think about in particular is a bivariate normal distribution for reasons which will become clear. And this is something which links the distributions of x and y. So bivariate normal distributions, multivariate normal distributions get used an awful lot in the world of finance. You've got a whole load of asset classes or a whole load of securities and you're trying to model them. One of the most common ways of doing that is starting with an expected return for each of the asset classes, a volatility for each of the asset classes, and a correlation matrix between those asset classes. And then you can work out, based on the weights of whatever you've got, the expected return on your portfolio and the volatility of your portfolio. So it's a really nice, easy approach to modelling, and it means you don't even need to do stochastic modelling if you've got a single period model. If you haven't got any cash flows, it's really easy, it's great. So a lot of people use multivariate normal in modelling. To generalise to the multivariate model though, it's best to start with the bivariate model, because then you don't have matrices of correlations, you've got one correlation coefficient. So if you are looking at a bivariate normal distribution, linking say two asset classes, two parameters x and y, is defined by 5 parameters. Mu x, which is the mean of x, sigma x, the standard deviation of x, mu y, the mean of y, sigma y, which is the standard deviation of y, the typo, and rho of xy, the correlation between x and y. And these together can give you the joint distribution of f of x and y. Now we get to the deconstruction, because some of these things here, they actually describe univariate distributions. So mu x and sigma x, they give you the parameters for a univariate distribution. They tell you what the distribution of returns on investment x is, for example. Similarly, mu y and sigma y give you the distributions of investment y. So you can model them both independently, regardless of separately from this kind of joint distribution. Actually, you don't want to do that because the way they're linked is important. But you could think of a bivariate normal distribution as being two univariate normal distributions and something which joins them, and that something is a copula. So this is a way to a good point to have a little interlude about why we bother using copulas at all. And this is a question which someone did ask beforehand. Why would you use copulas? And it's a good question because the multivariate normal distribution, for example, is a really useful, simple tool which doesn't even require any stochastic modelling if you haven't got any cash flows. It's really nice, it's really neat, very scalable. You just don't need to think about it. But it's not perfect. One of the challenges with that, or any multivariate distribution, is that the data might not fit it. In very broad terms, if your data don't fit a multivariate distribution, then you might need to think about something else. So why might your data not fit a bivariate or a multivariate distribution? There's several reasons. The first is the marginal distributions might be different from one another. So it might be that you've got returns on your asset classes which are all normally distributed. But it might be you haven't. It might be that you've got some asset classes which have very fat tails. So you might want to model those using student's t-distribution with a fairly low number of degrees of freedom. Or it might be that you've got several which are all following student's t-distributions, but they've got different degrees of freedom. So you have some asset classes which have very fat tails and some which don't have very fat tails. Or you might find that when you're looking at your returns, some asset classes give really skewed returns. So they might tend to have fairly moderate levels of positive returns, but when they make losses, they make really big losses. So if you've got this, then trying to fit things which have different marginal distributions into a single multivariate distribution is very difficult. Or it might just be that you think that the marginal distributions might be quite similar for various different asset classes, but the thing that joins them together is quite different from how they behave together. So for example, it might be that you think, well, to all intents and purposes, all my asset classes are normally distributed. All the returns are pretty much normal. But if I look at the risk of things going wrong together, so the risk of making a big loss from all of my asset classes at once, that's much higher than I'd predict from a bivariate or a multivariate distribution. So it's not so much about how fat the tails are for the individual asset classes, it's how jointly fat the tails are. So what that might suggest is that you might want to use a normal distribution for each of your individual asset classes, but when you're putting them together, you might want to use a copula which has jointly fat tails, so something which isn't based around the normal distribution, but is maybe based around a t-copula, or maybe some of the other copulas that we'll look at later if we have a chance. So the main reason to use copulas is for one of these reasons, that if you try to squeeze everything into a single multivariate distribution, you are obscuring some of the problems that you might have with the underlying data. So what you need to think about is how much does this matter? How important is it that you use something like a copula? And that comes down often to how important what happens in the tail of the distribution is. So if you are looking at a portfolio and you're really concerned about losses beyond a particular level and extreme losses, then using the right copula becomes very important, because if you underestimate those joint risks, then you risk underestimating the amount of capital you might need to hold or how much risk you can take. The best example of this, and I'm not going to go into technical details about it, but if you go back to the financial crisis and you look at CDOs, collateralized debt obligations, which were essentially groups of loans, say, which were all put together into a single pot, and people made different returns depending on how much risk they wanted to take by investing in these pots. And these were modelled using a normal copula. So basically the middle bit from a multivariate normal distribution, which severely underestimated the risk of lots of things going wrong together. So if you'd used a different type of copula, you would have priced these things very differently, and the point at which losses happen for people who want to take less risk would have been much higher up, and the price you would have had to pay to get a lower risk would have been much higher than was advertised.